Okay, consider a charged capacitor, okay, and it is connected to an inductor. All right. Now, so this combination, it's L and C, correct? Now, what we have here is, see, a charged capacitor. So this will start discharging, meaning the charges will keep on going to the inductor, correct? Now, what's happening as the charges keeps on increasing? That means the current is flowing through the inductor. The current is increasing gradually. Now, what happens in an inductor if the current keeps on changing? The magnetic field is induced, correct? So, what we have, the capacitor is discharging and the magnetic field in the inductor is increasing, correct? So, the capacitor discharges completely and the magnetic field in the inductor will be at maximum magnitude, right? Then what happens? The magnetic field, there is no source to increase the magnetic field. So the magnetic field will keep on decreasing, correct? As the magnetic field keeps on decreasing, what happens? So there is an induced EMF, correct? The induced EMF will be in the opposite direction, correct? So the current will keep on going like this. Current meaning the charges. The charges will flow, the movement of charges. Okay? So the charges will keep on moving in this way. So the opposite side of the capacitor will now become positive, correct? Because of the induced EMF which is coming in the opposite direction. So the magnetic field lines, they will keep on decreasing and the capacitor keeps on charging, right? So once the magnetic field completely discharges, the capacitor will be at maximum potential. Now what happens? Again the capacitor discharges, correct? So what is happening here? So the capacitor discharges, the inductor charges. Now what is the charging of inductor? Is nothing but the magnetic field is increasing. Because if you guys remember, I told you in like a long time back that in an inductor, the energy stored is in the form of magnetic field lines, correct? Meaning here, the inductor is basically charging, correct? So capacitor first charges, then discharges, the inductor charges, inductor discharges. So what's happening here? There is an oscillatory motion, correct? Like one is charging, one is discharging, one is charging, discharging. So what we have is LC oscillations. Okay, so this is what we call as LC oscillation. Now if you look at the graph, this is how LC oscillation will look like. Okay, so first charges, then discharges, charges and discharges. Now see, what we are considering is an ideal case, okay, an ideal condition, meaning the capacitor has no resistance and inductor has no resistance, and the wires also, they have no resistance. It's a pure capacitor, pure inductor. We're talking about ideal scenario. Okay, so in such cases, this is the graph what you're going to get. Suppose, let's say you take the normal condition. Okay, normal condition. See, in such cases, what happens? We are going to get damped oscillations. Okay, meaning because of the heat loss, what happens? The current will keep on decreasing and it will stop. Okay, so this is the damped oscillation graph. Okay, so we looked at about what is LC oscillation and then how it happens, correct? So now you will be learning how to derive, meaning a mathematical treatment for the same LC oscillation.